Yeah. Hello, everyone. We'll wait till a few more minutes. We'll wait for a few more minutes so that people can continue joining. Yeah. Good evening, everyone. We have 8 people. We'll wait for a few more minutes in case more people are on the way. And yeah, till then, if anyone has any immediate doubts from the sessions, please put it here so that we can talk about those before we start the class. Okay, I don't see any doubts, but I will monitor the chat to see if there is something. But yeah, we'll just wait for 2 more minutes in case people are still joining. Sorry. Okay, I think we can start. Let the other people join as it starts. So, yeah, again, welcome back, everyone. This is week 5 of your NPTEL course, and the particularly the problem solving sessions of your NPTEL course. So, for anyone who is joining for the first time, my name is Zenia. I am a PhD student at the Indian Institute of Science, and I have been conducting these sessions for last 4 weeks. I'm sorry there is some construction work in the background. If there is any issue, please let me know in the chat. But yeah, I am not able to control that at the moment. But yeah, as I was saying, these sessions are held every week so that it facilitates you to solve your assignment and understand the concepts. It gives you a recap of the concepts and also helps you to understand the assignments better. As usual, I've provided my email ID and also my website where I maintain all the links. So you can find the recordings of these problem solving sessions. There have been 4 already. And also you can find the slides for all the problem solving sessions that I've been doing. So I think some of you had mailed me with some specific concerns, and I think I have replied to them. So, yeah, please continue to mail me throughout the week if you have any particular concern or if you want any particular topic to be covered. I will try my best to incorporate it and to address them. And yeah, you can also, rather than mailing me, you can also, of course, bring it up during these sessions. These sessions are meant to be interactive sessions where you can, sort of understand more about the course also. So you're always free to interrupt the lecture and say that we can discuss something else instead. But if you have an agenda in mind, but yeah, for now, I don't see any immediate questions or anything in the chat. I had prompted a little bit earlier. So I think we can move on to the lecture. So as I said last week, sorry, one sec. Yeah, we have now moved past the more astrophysics and towards more nuclear physicsy parts of the course of the nuclear astrophysics course. And this week you particularly learnt about, of course, some discussion of resonant and non-resonant reactions as you had last class, but also you learnt about the different cycles of nuclear burning in the sense that there are chain, CNO cycle, and so on, and these all contribute to nuclear burning in the center of particularly our sun. So we have already discussed stellar evolution and hydrostatic equilibrium in some detail in the earlier first few lectures. So that time you know that the nuclear fusion at the center, which astrophysicists often call nuclear burning, is essential to keep the star stable and ensure that it continues its life on the main sequence. Also, you found that you can describe nuclei using the liquid drop model, which I think you would have all learned during school itself. But particularly, you might have something which is new to you might be the shell model. So just like how atomic orbitals and shells can be described in Bohr's theory and little advanced formulations of atomic models, we can also have a similar analogous but not the same kind of shell model for a nucleus as well. And we look at little bit the motivation behind the shell model and also what it entails and all that. So yeah, today's we'll just start off as usual by just having a recap of these concepts. So before we start, I just wanted to mention these things because it's kind of very interlinked. We're talking about nuclear physics and so on. So I'm sure that most of you already know all this, but in case there's someone who doesn't know, or to remind you, every interaction in the universe can be described in terms of four fundamental forces. So there is, of course, gravity, which is the weakest force, but is also the force that we are most, seeing in our daily life, because that is a force that's most apparent to us. It takes place on all length scales, starting from the smallest, interaction between two balls on Earth to the entire solar system, galaxies. Entire galaxies are held together because of gravitational force. So it is actually the weakest force among the four forces. Apart from that, you have the electromagnetic force, which is a force between charged particles. So gravity is between any two bodies, but electromagnetic force only exists between charged particles. Again, electromagnetic force is very important. The reason why when I hit the table, my hand does not just go inside the table is because there is electronic repulsion between the electrons in my hand and the electrons of the table, right? So yeah, there is a lot of electromagnetic force, of course, powers everything that we see around us. These two are forces you should be familiar with, but the forces that we'll be interested in today are the weak and strong nuclear forces. So those are the forces which play the most important role when it comes to nuclear physics. Particularly the strong nuclear force is what holds the nucleus itself together, right? So there is always this question of, if like charges repel, how come so many protons stay together in the nucleus? And we already discussed somewhat about this when we talked about the Coulomb barrier in the last class. So we saw that beyond a certain radius, there is a force which comes, which is attractive and overpowers the Coulomb force, and that is a strong nuclear force. The weak nuclear force comes in decays, and we'll be seeing a lot of the weak nuclear force, particularly when we look at the pp chain, for example. And weak interaction is usually what produces, for example, neutrinos, which also we had discussed at some earlier lecture. So yeah, astrophysics, as I said, is a very nice theory because it allows us to probe sometimes all of the fundamental forces together. So here is an image that I took from, I think, a Caltech website, where they have shown how in a stellar nursery or a nebula, which again we have discussed this in I think one of the early lectures, there is a presence of all the four fundamental forces working together to keep the nebula shining as it is. Okay, so I just wanted to give an introduction to the fundamental forces. I don't know why, one sec. Yeah. So to start off with, we can talk about the two kinds of ways in which hydrogen is converted to helium, right? It is not simply a matter of two hydrogen fuse and form helium. As you know, that is, if that was the case, we would not be any hydrogen in the universe, right? It would have all fused to helium. It is a reaction which requires a lot of energy and a lot of temperature, especially to fuse hydrogen to helium. And in fact, there are many fission reactors around, but there are no we have not been able to recreate nuclear fusion on Earth because the temperatures that are required and the way in which to confine the high temperature plasma is still a very much an open research problem. So that is something that plasma physicists, for example, are very interested in how to contain the material and keep it burning. But of course, nature is always one step ahead of us, has already figured out how to do that, and that's what we see in this sun. So you can see that the pp chain seems to have a lot of different kinds of branches, but essentially you can see that four hydrogen go in and two helium come out. Sorry, one helium comes out, and that is the overall reaction. In between there are some phases including the formation of deuterium, formation of the the isotope of helium with at mass number 3, and so on. And finally it forms a stable state, and you can see that energy is released during this process, and that energy release is of course very important because that energy release is what keeps the star stable. If this was an endothermic reaction as opposed to an exothermic one, hydrostatic equilibrium could not be satisfied and the sun would have collapsed a long time ago. So yeah, so it's important to understand the kinds of reactions that convert hydrogen to helium, because as we saw when we looked at stellar evolution, the main sequence phase is actually where a star spends most of its life, right? So understanding the burning process of hydrogen becomes very important in that case. So a pp chain is a very it's called a pp chain because basically it's proton proton. Hydrogen is a system with one proton and one electron, so we are only interested in nuclear fusion, means we just have to look at the proton, so that's why it's called proton proton chain. You can see that it's a very simple process. You smash two protons together to make deuterium, and you can see that this happens with the release of a neutrino and a positron. So this is a weak reaction. As I said, usually when you have weak interactions you see release of neutrinos, and this is one of the reactions which takes a lot of time when you compare with the other steps in the process. You can see that in this diagram as well. This takes around 1 billion years. And then you can see that after that one more hydrogen is required so that we can interact with the newly formed deuterium, which gives us a 3 helium, and we need to do steps 1 and 2 twice so that we have 2 helium nuclei. And finally, when you get the 2 new helium nuclei together, you get 4 helium, which is what we want, and it gives back your hydrogen atoms. So essentially you can see that we are effectively taking 2 protons and making a helium, because it at the end of the process you get back 2 helium atoms, sorry, hydrogen atoms, right? So if I write the overall reaction, you will see that this, for example, cancels this helium, and this helium will cancel, and overall you will get something like 2 hydrogen is giving 1 helium, right? So that is what we expect from mass number conservation and all that as well. But if you notice, this is I have included a very interesting note here, which is that this sort of path happens only around 70% of the time. What happens the rest, roughly 30% of the time? Well, what happens is sometimes the first two steps happen, but other elements can be formed. Okay, hello, you can hear me, right? I think there was some network. Okay, I don't know what happened. We'll just go back. Right. So, sorry. Yeah. So, yeah, this is what happens roughly 70% of the time. But there are, cases where other kinds of paths can happen. So, what are those other paths? So, to start with, we have the pp2 chain, which happens 31% of the time. So here you can see that one of course, this all these reactions are not happening in a chain, right? There are, while this step is happening, there are already helium 3 atoms for floating around, and there are helium 4 atoms floating around. So they may interact with each other to form beryllium. Okay, with release of energy, of course. And this beryllium can give rise to a lithium atom. And finally, this is kind of like a electron capture reaction. Again, this is a weak interaction. A good way to look for weak interactions is whenever there is a neutrino involved. And yeah, so when you can see that finally lithium reacts to the proton to give again two helium. So if you effectively look at this reaction, if you write down all the reactions and their chains and cut out the reactants and products, you will see that finally the end product is two hydrogen is giving one helium, and whatever is being produced gets used up in another step. But there are certain other chains which are also possible, which is what I wanted to show you. And a very rare chain, 0.3% of the time, is that beryllium, instead of capturing an electron to form lithium, can actually form boron. Sorry. So boron can then beta decay to beryllium, and that can further decay to two helium atoms. So you can see that there are different kinds of chains, and as I mentioned again and again, the main thing is that they all result in the same thing, which is the formation of helium. But it is interesting because we do see signatures of some of these other elements, and you might be puzzled as to how beryllium or boron can get there in the first place. But the answer is that these are the in between steps of the pp cycle. So here is a sort of summary of all of the different mechanisms. You can see that the first two steps are the same. We have to produce helium, and then, as I said, around 70% or 69% of the time, you see that the dominant pp1 chain, which is what we expect, the two heliums fuse. Sometimes the helium which is formed, there might be some rogue helium, which helium 3, which actually fuses with helium 4 to form beryllium. And then that beryllium can either go through an electron capture and form lithium, or it can even interact with a proton and form boron. So these are these are the sort of three cycles for the pp chain that you do. And again, if you take the overall reaction, if you follow any of these branches completely, and you like see what reactants are being used up and what is left over at the end of the reaction, you will see that on the reactant side you have two hydrogen, and the product side you have two helium. Sorry, one helium. So that is basically about the pp chain. And this pp chain is what is actually happening in our sun right now, and that is the dominant mechanism, or the dominant mechanism is of course the pp1 chain. But yeah, this is what is actually happening to fuse hydrogen to helium in our sun right now. So the other famous cycle is called the CNO cycle. So CNO stands for, of course, carbon, nitrogen, and oxygen. But don't get fooled. This is also a way for us to produce helium from hydrogen. So again, we are going to be effectively looking at the same reaction, which is hydrogen fusing to form helium. But here the intermediate steps are taken by carbon and nitrogen and oxygen. So this is a nice diagram I found, where you can see how it's basically that the what can I say, the carbon, nitrogen, and oxygen are what are called catalysts in this reaction, because they take part in the reaction, but they get used up. They either, get used up or something. And overall reaction, you will not see carbon, nitrogen, or oxygen taking part in the reaction. So you can see actually that where can we start from? So I guess hydrogen and carbon interact, and then they release energy. It forms nitrogen. Then that nitrogen decays to positron and neutrino. So that's a beta decay. It forms carbon 13. Carbon 13, when it interacts with a further a hydrogen atom, it releases energy to form nitrogen 14, which further interacts with a hydrogen atom to form oxygen 15 with release of energy. Oxygen 15 is not stable. It beta decays and forms nitrogen 15, and that further reacts with hydrogen atom to form carbon and helium. So you can see that we are effectively having how many hydrogen atoms are going in and how many are coming out. So you can see that again the numbers are balanced, and we effectively get what is two hydrogen atom giving a helium. So I have written down the reactions. I mean, I have taken a picture and shown how the reactions proceed here. So you can see that we have four protons which are forming a helium. Yeah. So yeah, so this is again These decays take time or instantaneously? Okay, very good question. So again, as I said, weak interactions are known to take a lot of time. Okay, so it is not instantaneous. We will see actually about time scales in a little time. So yeah, just for anyone who's not seen the chat, Gopinath has asked if these decays are taking time or are they instantaneous. Nothing is instantaneous. There are a lot of uh, there is some time within which it happens. I can't tell you the time scale off the top of my head, but like if a element is unstable, for example, it will decay fairly quickly. But others, other interactions, it will take time, right? It depends on when a hydrogen and hydrogen will meet. So there will be that probability or that they have to meet. Then, of course, as you know by now, every reaction has a particular cross section. So there is a probability that even when two elements meet, that reaction should take place, right? So those kinds of things are important. That's why we cannot just do fusion by taking two random hydrogen atoms from the air, because we have so many hydrogen atoms around us. Why can't we just do fusion? The reason is the conditions have to be so favorable for fusion to happen within a reasonable time scale. Okay, so that is the answer. And generally weak interactions take time, because that's the norm when you would compare with the other reactions. So the way that for example, there's this particle called the kaon. The way that it was discovered itself was because there's this weak interaction which was taking a long time when we compare with some other interaction. So they found that, the kaon, I think, I don't remember the correct story, but basically there were two formation channels for the kaon. And they found that, what they expected was a certain time scale, but then they found that the kaon that was also produced to another time scale which was much longer than what they expected. And then they realized that, okay, there is some weak interaction which is happening, and that led to the discovery of the kaon. Not really the discovery of the kaon, but the discovery of a property about the kaon called strangeness. So yeah, nuclear physicists are very interested in time scales and all that, because when something does not follow the predicted time scale, for example, then it can reveal some interesting properties about that object. So yeah, so this is the CNO cycle, and yeah, you can see that again CNO also has a branch off where, again, these are, there are so many atoms. It's not necessary that only the atoms which I want to interact will interact, right? Not that the hydrogen will also always go and interact with another hydrogen. So there are some other things. So that's why we see this branch off of the CNO where fluorine is produced as one of the catalysts as well. So how much energy is released? So yeah, I think I misspoke before. I kept saying two hydrogen, but I meant to say four. Okay, obviously four hydrogen have to be there, otherwise we will not get helium. Okay, so I'm sorry about that. I think I misspoke before. But yeah, we need four hydrogen to form a single helium, because we know that mass number and proton number have to be conserved. So I said two just looking at the reaction like this, but of course that is a very simple mistake to make, because in the actual effective reaction you have to do both these steps twice. So there will be two times of these reactions and then this reaction. So actually it is four times protons will give one helium reaction. Okay, so I think I misspoke just like that. So just ignore when I said two before. So yeah, four hydrogen and of course two electrons. So yeah, again, if you take any of these reactions, I encourage you to do it. You just sit down and like write all the reactions including the duplicates in full, and see how many hydrogen is needed for one helium. You will find that everything except two hydrogens and two electrons, sorry, four hydrogens and two electrons get cancelled, and we get this four helium. So then you can find what is the Q value of this reaction, and we know that the Q value should be positive, because a positive Q value represents, exothermic reaction. And as I explained before, we require these reactions to be exothermic, because otherwise we will not attain hydrostatic equilibrium. The star will not be stabilized against gravity. So you can see that if you do the calculation again, I think you are all very much experts in doing this kind of calculation by now. You know the mass of the hydrogen is essentially the mass of the proton, so that will be, whatever, 1 amu. And then this will be 4, and then if you put the correct values and then you multiply by the c squared factor, you will see that around 26 MeV is released every time you fuse 4 hydrogen atoms. So you can see that this is equivalent to about 0.7% of the mass of the original 4 hydrogen atoms. So every time 2 hydrogen atoms are released, less than 1% of that energy is released. Right? Most of the energy, 99% of the energy goes into making the helium atom, but less than 1% is released. But this 1% energy release is again very important, because that is what essentially stabilizes the star. And in the star, in our sun, we have so many number of hydrogen atoms that this energy kind of adds up and provides us enough energy to stabilize the star and maintain hydrostatic equilibrium. So, if you recall from our very first problem solving lecture, we did a rough calculation on how long the star's age will be, or how long the sun will last before it dies, based on its supply of nuclear fuel. So you can see that in that we had used this factor of 0.007, right? And that actually came from this value, which is that around 0.7% of the mass was released every time. And of course we had to put in some values for what is the mass of the hydrogen and the mass abundance and so on. So yeah, these are some other estimates which come from other ways, but I just wanted to explain this factor, which now we have also calculated by ourselves. So I will say that all of you please do this calculation and check whether this 0.7% number is correct. I can also make mistakes sometimes, so make sure that you verify and let me know if I have gone wrong. Okay, so in our sun, the thing is that we only really see the PP cycle. We don't really see the CNO cycle, and the CNO cycle only comes in really higher mass stars and advanced stages of nuclear burning. So you can see that here this is the temperature and luminosity plot, and you can see that the energy release of PP and CNO cycles are very much dependent on the temperature. So as I said, if we want a proper energy release to come from it, we need high temperatures. That's the reason why we have not had fusion happen on earth yet. We don't know how to. So problem with fusion on terrestrial conditions is when we heat up material to as hot as, so the sun's photosphere is around 6000 Kelvin. Inside it's going to be very very hot, like millions of Kelvin, right? So when we heat up material on earth to that much value, it does not become solid, liquid, or gas. It becomes into a state called plasma. Plasma is basically like a fluid or a collection of charged particles and ions, right? And it becomes very difficult to contain that plasma. And this is what plasma physicists work on in various institutes around the country, including IISc, is they work on ways in which to confine that plasma, maybe through a magnetic field or something like that. So that is a very active area of research. But as I said, nature is one step ahead of us, has already figured out how to contain the plasma and all that. So you can see that in the PP chain is, actually less dependent on temperature when we compare to CNO. So CNO, it is very highly dependent on the like very highly sensitive to the temperature, around T power 20. Some places I see T power 17. So it's around that, order of magnitude estimate. So you can see that beyond a point, the CNO cycle becomes very steep, because of course when we increase the temperature beyond a point, this goes as T to the power of 20. So the energy release will be much more. But in the lower stages, you can see that T power 4 is what is powering. So our sun lies somewhere here, and you can see that for our sun, this is again the same axis as this, energy versus temperature. You can see that the energy from PP cycle is a little bit more than the energy from the CNO cycle. And this is of course a log scale. So even though it looks like a small difference here, it's actually orders of magnitude. So that's why PP, we say that in sun-like stars and low mass stars like the sun, the PP cycle is much more efficient. Whereas when as you go to hotter stars or more massive stars, we see that around 18 million Kelvin. Again, if you go back to your stellar evolution, you know how to relate mass and central temperature, and you can see that For hotter stars, the CNO cycle is much more effective. So because they have higher central temperatures, you can see that the energy released from CNO is much more than the PP cycle. So so we can kind of compare and contrast these different relations. So that's about the nuclear cycles. Does anyone have any doubt before we move to nuclear models? Any doubts, immediate doubts? This is all, like, I think this has all been covered in your lectures. This is basically the two ways in which hydrogen can be fused to helium in stars, not just our sun, because you know that every star starts off burning hydrogen in what is called its main sequence. And as I said, the main sequence is the longest period of life in the stellar evolution. So it's important that we understand it to some good degree. Okay, so I don't see any other questions, so we can move to the next part, which is about the nuclear models. Okay, so before I go to this, basically, we understand the atom and we know that what powers the atom. To understand the atom, to understand the atomic model, what we really needed was, first of all, of course, we needed some quantum mechanics, but the force that is there in the atom is somewhat simple, right? In the sense that it's kind of like a planetary system. Not exactly like a planetary system. You know that Rutherford's model failed because it was, not fully applicable. But I'm saying it is like a planetary system in the sense that there is a central body, and that kind of controls the motion of the electrons around it, right? So there's some sort of central body, which is your, of course, your nucleus. And the nucleus, as you all know from Rutherford's scattering experiment, which I think you're all familiar with. Rutherford's scattering experiment tells us that most of the atom is actually empty, and most of the mass of the atom is actually concentrated in the nucleus, which is, about 5 times smaller than the atom, and it is at the center of the atom, right? So, I mean, not 5 times, 5 orders of magnitude smaller than the atom, right? So, if the atom size is usually around 10 power minus 10 meters, which is called an angstrom, the nucleus's size is 10 to the power of minus 15 meters, which is called a Fermi. So, there is 5 orders of magnitude. When I say order of magnitude, it means 10 to the power of 5. So, there's 10 to the power of 5, almost a million size difference between a nucleus and an atom. So, for all purposes, we can think of it as being like there is a central body which is controlling, how the atoms, electrons move around it. Of course, because we are in quantum regime, I have spoken about the transition between classical to quantum physics a little bit in all of the lectures, I think, actually. But yeah, because electrons are very small, small particles, we are actually in the quantum regime, and we have to be careful about things like quantization. So what quantization means is essentially that in an electron, in an atomic system, for example, you cannot just take a continuous spectrum of energy. The electron cannot have any energy it wants. It can only have energy that is corresponding to a particular, some particular set of values, and those were found by Bohr in not exactly in a quantum way, but in something that resembles quantum theory, in a, what is called now the old quantum theory. So, so the main thing that you need to remember whenever someone says quantum mechanics is that, of course, quantum mechanics, the word comes from quantization, which means that things are now discrete. So, the famous example that people give is that imagine going up a slope, or imagine going up what is it, a flight of stairs, right? In a slope, you can just go up how much ever, you can go up 13.7 meters, but in a flight of stair, you can go up one stair, two stair, three stair, you can't go up 1.5 stairs, right? So that is the kind of difference between classical and quantum mechanics that you have to keep in mind. So why did I say so much about nuclear atomic physics? I just want to point out the difference between modeling an atom and modeling a nucleus. You might think that these are both quantum systems, these are both very small systems, we can kind of, draw analogies between them, and we definitely can. That's what we do when we prepare this nuclear shell model, for example. But the point is that there are differences, right? And when you if you just like that transfer one to another, that is also wrong. So yeah, so what I was saying is, in the nucleus, you don't have any such central body that is controlling the dynamics, right? All the nuclei are moving around each other, and they are, as I said, held together by the strong force. So then how do I define the nuclear forces inside, and how do I study the motion of any one nucleus? So for that we have to do some approximations, and that is what we are going to see. So before we go to all that, we can first look at the liquid drop model or the semi-empirical model. So this is called semi-empirical because it was based partly on experiments. So there are two kinds of theories in physics. One is, from first principles, where you write down a formula which is, from a theory perspective. The other is an empirical thing where you kind of try to look at something from the point of view of an experiment and then try to fit the data to some sort of formula. So this is semi-empirical model in the sense that some of it came from experiments, like the values of the coefficients, for example, but a lot of it was motivated by theoretical considerations as well. Okay. So this is again, you should have seen this. So this EB is the binding energy of the nucleus, and you can see that there are a lot of terms which contribute with different signs to the entire thing, right? So the idea was that a nucleus behaves like a liquid drop, and I put the animation there, and it has contributions to its energies from all these different terms. So one is the volume term. Of course, the bigger a nucleus is, or the bigger a drop is of water, then it will have more energy, right? It will contain more energy because there will be more forces between each of the protons and neutrons. So that was just based on the number of protons and neutrons, total number of protons and neutrons which are there. You have a volume term, because if you have more protons and neutrons, you have more forces between them, and that keeps you much higher. Then you have a surface term. So this is again motivated mostly from liquid drop perspective. You know that at the surface of water, for example, so I know that, suppose you can imagine a bottle of water like this. You can see my screen, right? So this is my bottle of water. You know that if I pick up a water molecule here, it has interactions with all the molecules which are around it, right? It has forces in it. You can imagine hands reaching out as the force, attractive force. The attractive force, it has hands reaching out in all of the directions. Whereas if I take a water molecule here, which is on the surface of my water bottle, or surface of the water in the bottle, you can see that the hands reach downwards because there are molecules to play with, but upwards, when it reaches, there are no more water molecules, right? So the surface energy is kind of different when we compare to water in the bulk. And that is what the surface term comes from. So you can see that this is a surface term, and it comes from, again, if you have learned about fluids, you definitely would have come across this concept of surface tension. Sorry, has someone unmuted? Okay. I think okay, I see a question in the chat in the meanwhile. Volume is independent of the number of particles inside the nucleus. So, no, that is not true, right? Density is independent of the number of particles in the nucleus. The volume is not. See, volume is the amount of stuff. So that does depend on how much of the stuff is. So I think you got confused because we mentioned density a few times. So density is mass by volume. There we are scaling out the volume from the mass, and in that case, it does turn out to be a very nice constant, which is called the nuclear saturation density. But here, if you remember, R scales as a to the power 1 by 3. And here we actually have uh, R cube, because it's a volume. If you just consider a 3D shape, any 3D shape, let's just consider a sphere, it's going to be R cube. R cube will go as a power 1 by 3 to the 3, and that's why we get A. So does that make sense? Yeah, okay. I see that you have said okay. So yeah, volume and density, don't get confused. Yeah, so why does the surface term depend on two-thirds? Can anyone explain, or can anyone guess? Can anyone tell me why the surface term has a power a to the power of 2 by 3? Yeah, a to the power of 1 by 3 squared is correct. But why is it 1 by 3 squared? Why should it be square? That's kind of what I was getting at. Radius squared. Okay, good. So yeah, as Vivek says, as I told you, when I consider the surface term, I'm only considering the cross section, right? I'm only considering that surface, and that has we are not considering the entire volume of water. We are only considering an area at the surface. The area will be having dimensions of r squared, so that's why we get a to the power of 2 by 3. So the formula, maybe I can write it here so that when you refer later, it will be easier for you. One sec. Insert equation. I'll just write the r a power 1 by 3 here so that in case when you're looking back and if you forgot, it'll be easier, I guess. So let's just, yeah, if you remember, okay, sorry. So if you remember this formula, everything in this liquid drop model will make sense. You will not have to memorize the powers of A, right? You can, it's up to you. But I'm saying that even if you can suddenly not recall one of the powers of A, you will be able to because you can rationalize it using this. So R power A power, R2 is proportional to A power 1 by 3 is very important. So I see that some other people have also given the answer. So very good, you all understood the concept. So the next two terms, one is the Coulomb term. So the Coulomb term is again very important. The Coulomb term basically tells you that even though I told you that Coulomb barrier has been overcome, we are now in a nucleus which is bound, there is still Coulomb repulsion which is between the protons. And you can see that that tends to decrease the energy. The surface term also tends to decrease the energy because I'm always overestimating those particles which are having extra energy from the particles on top when there are no particles there. Similarly, the Coulomb term also overestimates the, like, it gives a negative contribution. And okay, so there is an important point here, which is that what is the energy of a stable nucleus? Is it positive or negative? Can anyone put it in the chat? The energy of a stable nucleus. Will it be positive or negative? Answer in the chat. Someone. Okay, someone says positive. I'm asking about this EB term. If huh. Okay, I see both positive and negative. Okay, one more person says negative. Others, just admit. Okay. Okay, I see more of you saying negative. That's good. So, Ajay, it's not positive, it's actually negative. But I can see your confusion because this formula seems to be indicating that positive, right? But the reason is that this is kind of based on the absolute value. Okay, so don't take this as, that means that the energy is positive. This is the absolute value calculation. Whatever we calculate, we have to put a negative sign. Why should it be negative? Because when it's just a convention in physics, right? It's like when you solve your gravity problems, for example, right? If you're dropping a ball downwards, right? If you define your y-axis to be increasing like this, then you'll find that the ball has a negative displacement. Whereas if I define my zero to be here and my y-axis to be down, then I'll find that the ball has a positive displacement. The physics has not changed. The ball is still going down only. It's only that the way that I'm describing it through the mathematics has changed a little bit, and because of that, I get slightly different answers. Doesn't mean one person is right and one person is wrong. In the same way, Ajay is not necessarily wrong. If you look at this formula, you will see that the energy seems to be positive. But the convention in physics that most people agree on and what you will see in textbooks is that the energy should be negative. So in that context, this should be an absolute value. And then we should put a negative sign. Why is the value negative? So the convention is such that the energy at infinity is taken to be zero, in the sense that when the protons are infinitely separated, they are taken to be zero, but when they are bound together, they have a negative energy, and that negative energy represents the fact that I have to provide some energy to make separate those two protons, right? So if two protons are held together, attracted to each other by this strong force, and you would have seen this in our Coulomb barrier plot also. The Coulomb repulsive part was above the x-axis, whereas the attractive strong nuclear force part was below the x-axis. So this just shows that when I have two protons which are held together by an attractive force, their energy has become negative. And I know that the energy at infinity, when they are infinitely separated, which means they are not interacting anymore, is zero. So that means I have to provide that energy to separate those. So it's like that's what's happening. So when you calculate, for example, when you know, I said, for example, 0.7% of the mass of the original hydrogen atom is released, right? So here it's like I didn't have to provide an energy. So that is the point of this. So you can see that if I take it as four, the reactants are more massive than the helium atom, so it releases energy. So this is the kind of thing that you have to think about, okay? So yeah, so the point is that we are just looking at the absolute value contributions to the binding energy, and whatever value you get from here, you have to write with a negative sign to indicate the fact that you have to actually put in some energy to release a nucleon from that bound. So if a nucleon is very stable, then it will have a much more negative value, right? If you see that E by N plot, which you will be familiar with, the binding energy per nucleon plot, it peaks at iron. And iron has a high negative uh, binding energy because you have to provide energy to ion to break it apart. Okay. So if something has, so everything in the universe wants to minimize its energy. If something has a lot of positive energy, in another way I'm saying, something has a lot of positive energy, it will try to get rid of that energy and come to a ground state. So the ground state is always negative. Okay. So I think we looked at volume term and surface term. Now we can look at Coulomb term. So again, Coulomb term is depending on, so this is something that comes from only the protons. And that is why you can see that only the proton number Z is playing a role. Obviously, the atomic number will, the neutrons will not play a role. That's why we don't have to use A. But still A comes in the denominator. And why does A come in the denominator? Well, I have written the answer there. Because as you know, between two protons, the energy energy goes as 1 by r, and here r is a power 1 by 3. So again we have a coming in here, and here z into z minus 1 is just a factor that tells me that, see, if I have four protons, then there are so many combinations, right? 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4, like that. So it's a combinatorics thing, like it's nc2, if you're familiar with that kind of thing. That factor is coming here, and if there's any, like, it should be nc2 will be z minus 1 by 2. That 2 has been absorbed into these coefficients. So these coefficients are actually what makes the liquid drop model a semi empirical model, because what they did was they wrote down this equation, like I think it was Weizsäcker who came up with this equation. So Weizsäcker writes down, and I'm sure there are other people but I don't know their names, but yeah, Weizsäcker writes down this equation and he says, okay, if we want to fix the coefficients, we have to do experiments. So they do experiments and they find what should be the value of the coefficient so that it can reproduce the energy in the correct way. So that's why it's semi-empirical. Okay. So an asymmetry term comes because of, because you will notice that that in the lighter elements, at least, the neutrons, it will usually be that the atomic number is twice the mass number. So like oxygen 816, nitrogen 714, so many examples, calcium 1020, and so on. So or is it calcium is 2040, I guess. Point is that in the lighter spectrum of elements, you will find a lot of elements which have this sort of asymmetry term, which asymmetry term basically tells you that symmetric nuclei are a little more stable. And in that sense, okay, I think someone has a question. Someone has raised their hand. Yeah, please unmute and go ahead.
Hello, ma'am.
Yeah, you're audible. Go ahead.
So when we talk about this binding energy, can be interpreted as the energy required to separate all these nucleons?
Yeah, that is exactly the interpretation of binding energy. Correct.
Yes. So ma'am, then when we are talking about this energy, so say if you have 15 nucleons, 15 nucleons, so are the energy, that is the average energy that is required to separate these nucleons by one, or is it just how will you interpret it as? Because since these nucleons are bound to each other with a strong force, then is it to get
Yeah,
out
so
one nucleon,
yes.
or is it in general?
So that is exactly why there is a binding energy per nucleon calculation. And in most places, what you will see is there will be EB by nucleon, right? By A. Usually there will be a divided by A throughout. If you see those famous graphs, they will usually already be per nucleon. So this gives you the overall energy, as you rightly said, to completely remove all of the nucleons away from each other, right? That's why I have to consider the combinatorics of all the nucleons and all that. But usually what is practically helpful for us is the binding energy per nucleon. And you kind of, when you take it per nucleon, you're kind of averaging that energy among the entire distribution. So that's why you can't see, if I just took the volume term, then averaging would be a bad idea. But here I've already, sorry, taken care of things like the surface nucleons have less energy. I've taken care of the fact that there is some Coulomb energy repulsion between the nucleons. I'm taken care of the fact that, is that A is equal to 2Z kind of nuclei are more stable. So because of that, this gives me a sort of average energy for all the nucleons, and that's why I can divide and get the energy per nucleon. So does that make sense?
Yes, ma'am. So if you
Okay.
give that kind of energy, that means you can actually separate every nucleons of its bound state, right?
Yeah, but if it's a very stable nucleus, you will need a lot of energy to be provided. So that's why, for example, I told you a few classes back about stellar evolution. We can fuse up to iron inside stellar cores, but every element above iron has to be done in some explosive process like a supernova, because they require those high energies to, destroy those elements. Iron is very stable. Just those small temperatures of fusion will not remove, break apart an ion nucleus. So you need those, extremely energetic events like supernovae to break apart an ion nucleus. So that is the kind of idea. And we'll talk about stability a little more when we talk about shell model also. So I think that answers your question, I hope.
Yes, ma'am. Yes, ma'am.
Yeah, okay. So yeah, and the last term which is there in this liquid drop model was a pairing term. And the pairing term was motivated by the fact that, as Vivek says, one way to measure the stability of nuclei is to look at this binding energy. And as I said, more negative binding energy means it's much more stable. Basically, if I have minus 20 as my binding energy, that means I have to give 20 MeV to break apart. If I have minus 50, that means I have to give 50 MeV. So obviously, minus 50 is much more stable when we compare to the minus 20 case. So people observed in experiments that it is, you know, as I said, this is semi empirical model. People observed that, when both the atomic mass number and the proton number are even, then they are much more stabilized. So you can see that when both are even, they get a sort of boost in the energy from this pairing term and the negative case. So people did not have a good idea about why this was. They said that it's because the nuclei are neutrons and protons are paired up, but also there was this kind of thing called magic numbers. So you know that in your atomic physics, for example, we say that octets are stable. So why do we have these different kinds of chemical bonds? Chemical bonds happen because there are elements who don't have complete octets, right? So they have to form their octet by binding with one or the other element. So that's why people, again, as I said, everything in the universe wants to go to the most ground state, the most stable energy state. And what we see is that for atoms it is the octet state. But we saw that for nucleons there were actually magic numbers. So it's not just 8, there are a series of numbers where it seemed like the nuclei which have those numbers are particularly stable. And this was not really explained by the liquid drop model, because liquid drop model does not give preference to any one number or the other. It says that there are all these factors, some of them contribute positively. By positive, I of course mean negative because of how energy works, and some of them contribute negatively to the energy. And we just have to fix the coefficients from experiment. And liquid drop was very successful. It explained fission, for example. You can think of fission as when a drop of water gets too big and its energy is too much, its surface tensions now cannot hold it together, it will break into two drops. Like, so there are models for fission and fusion with the nuclear liquid drop model, and it worked well. But again, these fundamental questions of why it should be that particularly even nuclear stable, or even why the magic number nuclear stable, was not addressed. And that's why we went to the shell model. So as I said before, there is a fundamental difference between atoms and nuclei, which is that when we look at atoms, we can say that all the dynamics is controlled by a central force, which is given by the Coulomb repulsion of the electrons and the protons. But in a nucleus, I don't have any such particular pocket of density. I have everything moving everywhere all the time, right? So to proceed with the shell model, how do we then make a shell model, right? It's not really moving in shells around a central point. So then what I do is I make a very important assumption. And this is an underlying assumption of the shell model, which you have to remember, right? And turns out that it's not a very bad assumption on the other hand. But I will tell you where the shell model fails in a bit. But again, so the assumption is that every nucleon moves independently in a time average field produced by the remaining nucleons. So that means that imagine a nucleus, imagine iron nucleus, which has 56 nucleons, if I remember correctly. I pick out one of the nucleons, say nucleon number 20, right? So I know that everything from 1 to 19 and 21 to 56 is exerting some force on 20, right? So I'm not going to care about any of the other nucleons. I'm just going to look at 20, and I'm going to say that 20 is going to move independent to how 1 is moving, how 2 is moving. It only depends on the field which is produced by the remaining nucleons. So it's kind of like if I take 20, if I know exactly what the forces are, and I code it up in a lab, and I pluck out 20 and I put that in that system, there should be no change in how 20's dynamics are. Does this make sense? So the reason why it has to be time average, because at a snapshot, of course, it might depend on how, the particle number 1 is moving. Maybe 20 will move along with it because they both are strongly attracted at that time. They are very close together or something. But if you take a time average, then you'll see that at some point, all the particles are interacting with each other and it doesn't matter. Okay. So essentially what I have done is, instead of looking at all 50 particles at the same time, I have picked up a nucleon and I say that every nucleon moves independently. So if I study the properties of this nucleon, I will be able to understand the properties of all the nucleons, and I just consider the other nucleons as the background in which this nucleon is moving. So now what I need to do is I need to model the potential or the field which is produced by the remaining nucleons. And why is the shell model attractive? Because again, just like how when an atom completes its octet, it becomes stable. That is why the noble gases don't react, right? Because they all have filled octets and we see them not reacting. Similarly, we can immediately then, if we have a shell model, we can immediately say that the reason why magic numbers are stable is because they are somehow fully filled states. Now, what are these states? That is the difficult part that we have to figure out. But this, once we accept that there are some sorts of states that have to be filled, then magic number comes out of the box immediately. And again, an important thing here about fully filled states being stable and the fact that states can be fully filled at all, the reason behind all that is that neutrons and protons are fermions. Just like electrons, neutrons and protons are fermions. I explained fermions in a previous class. So essentially, the thing that you need to remember about fermions is they obey the Pauli exclusion principle. So that is why new octets are stable, because they represent the fact that you cannot add any more electrons to the system without violating the Pauli exclusion principle. Similarly, when I say fully filled state, that means that according to Pauli exclusion principle, I have filled up that state. Okay. So right. So now this is a basic idea of shell model, is that I want to pick out a nucleus and I want to model the dynamics around it as a potential. So then the question comes of what potential. So again, these are deeply quantum systems. So I would suggest, and I have some recommended reading, but I would suggest strongly that if you are not very comfortable with quantum mechanics, that you don't need to understand like everything in quantum mechanics to be able to somewhat follow this. But if you are interested in this sort of thing, then you definitely need to brush up on quantum mechanics and things like angular momentum addition and spherically symmetric solutions and so on. But yeah, so there is a famous quote by a theoretical physicist. I forgot his name, but he says that everything in theoretical physics is theoretical physics is the art of modeling everything using harmonic oscillators or something. So yeah, theoretical physics is basically the study of harmonic oscillator in higher and higher complexity. So the quote goes something like that. And that's something that's very true, because harmonic oscillator is one of the rare cases So where the Schrodinger equation is exactly solvable. So the Schrodinger equation is what controls the dynamics in quantum mechanics. And what you'll see is for most potentials, the Schrodinger equation, you cannot solve it using a pen and paper. You have to put it into a computer. But there are a few systems like the hydrogen atom and the harmonic oscillator, which are exactly solvable. And we, theoretical physicists being lazy, we tend to use them again and again. So yeah, the first kind of thing that people did was they said, okay, maybe the well, we can represent the potential as a harmonic oscillator. But then we saw that, harmonic oscillator is simply not that good enough. Then we said that, or maybe a strong square well potential, which is another famous solution that comes in physics. So people tried these, but they saw that the magic numbers were not exactly, from theory and experiment, were not exactly matching up. So then we realized that, okay, so it is not a harmonic oscillator, it's not a square well potential, it's actually something in between both of them that seems to be fitting. And we have neglected one thing, which is a spin orbit coupling. So spin orbit coupling is an important quantum mechanical effect. It comes in atomic physics also. So if you've heard of something called fine structure of atoms and the fine structure constant, that comes because of spin orbit coupling, among other things. So spin orbit coupling basically is the idea that to, every uh, nucleon just means neutron or proton, has a spin. And they're also like kind of, you can consider them orbiting around each other. So those, each of those has an angular momentum. So every nucleon has its intrinsic angular momentum, which is what I'm going to call the spin. It also has an angular momentum by virtue of its motion, right? So those two are represented using different letters. The spin is represented using S, and the angular momentum, orbital angular momentum, is represented using L. And these two interact in such a way that it can produce some extra effects. It can break degeneracies, right? What do I mean by that? When something is degenerate, so I have used this word degenerate before in our course, but right now I'm using it to mean a very specific thing, which is that when two states have same energy, right? So actually what spin orbit coupling does is it breaks degeneracies, right? So you can see kind of here. So you can see that this 1p state actually consists of these two states, 1p half and 1p 3 by 2. And if we don't consider spin orbit coupling, you can see that both of them have the same energy. So this is something called an energy level diagram. So as we go up, the energy levels are going higher. So this is a state with higher energy, this is a state with lower energy. You can see that if we don't consider spin orbit coupling, both of the energy levels have the same energy, right? They are both overlapping on each other. And we would not know that there are two energies. But if we consider spin orbit coupling, because of this interaction between the spin and the angular momentum and the orbital angular momentum, you can see there is a slight difference between the energies. 1p half and 1p 3 by 2 are divided. You can see that as we move to higher and higher orbits, some of these divisions are significant. Like this one, it one of the values goes here and one of the values goes here. So you can see a clear division. So actually what was happening was we were counting the magic numbers based on a simple assumption that all the states, all the energies are at the same in 1p, for example. But actually there is a division of energies, and it can be that in this state these electrons are actually contributing to the next level. Sorry, I say electrons, I mean nucleons, contributing to the next level, and maybe some are contributing to a lower level. So why is energy and number of nucleons related? Because again, as per Pauli exclusion principle, there are only a specific number of nucleons which can have a particular energy level or exist in a particular state. So state, energy, number, these are all linked together. So essentially every state has a particular energy, and also every state can admit only a particular number of nucleons. And that reason is because of the Pauli exclusion principle, which comes because nucleons, like electrons, both neutrons and protons, are fermions, right? So there is a lot of things going together here. So again, if you don't know quantum mechanics, or if you're not that familiar with it, this might sound a bit crazy, but trust me, this works. So this is why quantization that I'm talking about, right? It cannot just exist in any energy it wants. There are a particular number of elements, there are a particular number of energy levels, there are a particular number of states, and there are also a particular number of nucleons which can go into each state. Now, one thing to keep in mind, One thing to keep in mind is that when I write 2 here, that means 2 nucleons can go. So when I say 2 nucleons can go, 2 neutrons can go, 2 protons can also go. So Pauli exclusion principle applies to a single species, right? So it does not mean that an electron and a proton cannot occupy the same state. That does not matter, because neutrons and protons, sorry, I keep saying electron, I mean neutron. Neutrons and protons are non-identical particles. So, when I write 2 here, 2 can be 2 neutrons and 2 protons can exist at the same time. Okay, so that's something to keep in mind. So in that sense, you can accommodate 4 particles here, but 2 of them are neutrons and 2 of them are protons. So that is the idea. And of course, according to your atomic physics, once you know what the energy states are, it simply becomes a matter of writing the configuration like you do in your atomic physics. So in your atomic physics, you write your electronic configuration according to Aufbau principle and Hund's rule and so on. You have to do the same kind of thing. Obviously, the lower energy states will be filled first and then the higher energy state. But here, because the spin orbit coupling is very significant, we have to take care that we fill the lower energy states and higher energy states while keeping in mind that the broken degeneracies. Okay, so I've said a lot of things. So I'll just give a 2 minute pause here. If anyone has any questions, we can answer them. But I will be explaining a little bit more. So yeah, we can also have the questions after that. But yeah, if you have any immediate questions, please ask right now. Okay, good. I don't see any questions, so I can think we can move on. Vivek, I think your hand is up, but I don't think you have a question. Is it from before? Yeah, I don't think he has a question. Yeah, okay, cool. Says no. Okay, I'm going to the next slide then. Okay, so this is a bit so much information is given, but this is going to be very useful for you when you solve your questions. So again, you can see that this is the same diagram as before, and this multiplicity of states tells you how many of the atoms are, how many, I keep saying atoms or electrons, I'm sorry, how many of the nucleons are allowed in each state. So you can see that magic numbers are exactly the ones where they fill an entire shell, right? So 2 and then 8 and then 20. So you can see that when they cover an entire thing, quantum energy state, that's when you call it closed shell, is called a magic number. Okay, so each state in the nuclear shell model is described by 3 quantum numbers called n, l, and j, which is represented like this, nlj. You can see that's what's written here. So these are quantum numbers. I think you already have come across quantum numbers when you did atomic physics, the principal quantum number, spin quantum number, and so on. So a lot of overlap is there in the sense that, for example, the angular momentum states are labeled by the same letters as we do in atomic physics. So s orbitals are angular momentum 0, p have L1, d is L2, F is L3, and G, H, it just goes on. Now, the important point is that N, which is the in atomic physics, N is the principal quantum number. And for a given N, L can take some restricted values between, for example, if N is 1, then you can only have one S, right? You cannot have one P or one D, because L can only take between 0 and N minus 1. That is in atomic physics. In nuclear physics, there is no such restriction. Again, this comes from the fact that the potential we're dealing with is a little different. In atomic physics, the potential we're dealing with was a purely Coulombic potential, whereas here we have a somewhat of a modified potential because of the strong nuclear effects, right? So you can very well see states like 1D, 1G, 2D, which do not exist in atomic physics. So that's why I said that we can draw analogies, but we should be careful not to, like, just like that, transfer everything from atomic physics to nuclear physics. So best technique to memorize the proton neutron filling state to find Gn parity. Yeah, I'm sorry, you have to memorize it. I can tell you some of the trends that are there, but yeah, it is not as straightforward as, I think in atomic physics you have those nice diagrams from the Aufbau and Hund's rule, but here I don't, as far as I know, there is no such quick way to memorize it. But I think if you memorize up to say 50, up to here, it is enough. That will that will be good enough for you. Some of the things that you can see in the fine structure splitting is, for example, always the state with higher J comes below energy when you compare it to the state with the higher lower J. So you see one three halves, 1p 3 half lies below 1p half, 1d 5 halves lies below 1d 3 half, and so on. So that is one trend that you can see, and I'm sure that when you start looking at it, you can also see other trends. But yeah, there is no straightforward way. Again, this is again a place where atomic physics and nuclear physics cannot be straightforwardly compared. So yeah, in case people don't know what J, L, and all are, so I said N, L, and J. J is basically the quantum number which corresponds to the total angular momentum, which is orbit and spin. So as I said, there are two angular momentum in play. One is because of the intrinsic angular momentum of the nucleon, and the other is the spin angular momentum. Sorry, the orbital angular momentum, which comes because of its motion. Now, when you add angular momentum, it is a vector addition, and it is not like just adding 1 plus 2. Okay, angular momentum addition is a very important topic in quantum mechanics. You will find chapters on it in books, because this is a vector addition, and you know that angular momentum states are also quantized. So when I have L as 1 and S as 2, the answer is not simply 3. There are actually number of answers. So J can take values from L minus S to L plus S in integral spins. And of course, S is always half, because we are only considering nucleons, which both have, neutron and proton, whichever you consider, both of them have spin half. So I've given an example here. If you take the state n is equal to 1 and L is equal to 2, then J can take values from 2 minus half to 2 plus half in integral spin, in integral step. That means 2 minus half, then 2 minus half plus 1, 2 minus half plus 2, etc., till you reach 2 plus half. And in nuclear physics, it always turns out that you will only get two states corresponding to every L. The N does not matter. Okay. L is only what matters. So you can see that 2 minus half and 2 plus half, which is 3 halves and 5 halves. And these are the states 1D 3 by 2 and 1D 5 by 2, which you can see in this diagram. So how did I get D? Just look here. You can see that D is what corresponds to L is equal to 2. Okay, so this is basically how you write down the states. So I've already told you how to do it. Can you list out all the states which have n is equal to 2, L is equal to 1? This should be very easy. I've already told you all the information is on the screen. So let's just quickly do it so that I can see that you have understood. Please put your answers in the chat. I don't see any answers in the chat. Did you understand the question? For n is equal to 1 and L is equal to 2, I got the answer that these are the two states, right? Like that, for n is equal to 2 and L is equal to 1, I want you to find what are the states. Usually for a given n and L, you will get two states. I can tell you that also, if it makes it simpler. Okay, 1 half and 3 half, but that is not what I asked. I didn't ask you for the J value. I asked you for the state. So 1 half and 3 half is correct, but I want the state. So write it in this NLJ formula. Or format, not formula. Okay. So I see someone has written 2p half, and I think you made a typo, 2p 3 by 3. You're getting three states, or is it a typo? 3 by 2, yeah, okay. 2p, 2p half, and 2p 3 by 2. Okay, I mean 2p half and 2p 3 by 2 are the states. So I think, yeah, I think rest of you should also be able to do it. So again, n is equal to 2 gives you the n value. L is equal to 1. If you look at this, if I have basically given you the answer here. P is what is L is equal to 1. The only thing you have to do is remember that you have to take 1 minus half and 1 plus half. So that's half and 3 by 2, as your friend said. So yeah, so the answer is 2p half and 2p 3 by 2. Does anyone have any doubt in how this answer came or did not understand? I can say it again. If anyone has any doubt, please put it in the chat now. Yeah, okay. I don't see anyone. So I hope that more of you will answer. I again don't want to prompt everyone to answer every time. So please answer in the chat whenever you're asked. Okay. So as your friend, one of your friends said, in anticipation, one of the things that is very useful from the shell model is we can find unpaired nuclear matter. Sorry, you can find the properties of nuclei, particularly the spin and parity. So I'm saying that unpaired nuclei are what matters, because those which are paired will not. It's just like in atomic physics, right? When we take the periodic table, what determines the chemical character of an element is its valence electrons. It's those unpaired electrons that take part in reactions and all that, because unpaired electrons are desperate to be paired with something, right? So the same way, unpaired nuclei are what matter. So we don't have to consider those filled shells. We only consider the unfilled shell when we talk about the overall spin and parity of a given nuclei. So as I said, remember the sequence of filling states in terms of energy. So you go from 1 is half, then 1p 3 by 2, 1p half, 1d 5 by 2, 2 is half, 1d 3 by 2. Try to memorize if you can at least until 28 or 50, because that will be very useful for you from the exam point of view. I don't have any immediate trick for you to remember. I'm very sorry. But again, there are some things that you can remember, like the spin. The larger J values are always lower energy when compared to the higher J values. Again, these are things that come in a full nuclear physics course, and I don't know how to immediately give you in a catchy way. And then also the question comes of how many nucleons can I fill in each state. So each state NLJ has a multiplicity of 2j plus 1. Multiplicity means how many nucleons go in each. So you can say that 1 s half has 2 nucleons, 1p 3 by 2 has 4, whereas 1p half has 2. So this means that 3 by 2 into 2 plus 1. So you see, if j is half, then we see 2j plus 1 is 2. So 2 nucleons can be present in that state. Again, when I say 2 nucleons can be present in that state, 2 neutrons and 2 protons can be present at the same time, because the Pauli exclusion principle takes care of only the same kind of identical particles. And if J is 3 halves, you can see that 2J plus 1 is 4. Again, the number multiplicity is not dependent on this L value or this N value. So you can see that 1 s half has 2, 1p half also has 2. Similarly, 1p 3 by 2 has 4, 1d 3 by 2 also has 4. So only J matters in multiplicity. So why this multiplicity comes is a exercise that I encourage you to do. It's actually just a counting states problem. So you know that there are certain we can only have all the what is it called, quantum numbers to be unique as per the Pauli exclusion principle. I have not put that exercise here, but I encourage you to do it. Just go and check how you can find this 2j plus 1. You can derive this formula. Maybe we can discuss it in the next class. So, and parity, finally, the other concept is parity. So parity is basically a quantity which comes when you look at reflection symmetry, right? So you know that again we are talking about quantum mechanical objects. Everything is represented in terms of wave functions. So depending on whether the wave function is odd or even, we say that the nucleus has an odd or even parity. So, of course, nucleus does not consist of one wave function. Each of the nucleons in the nucleus has its own wave function, right? So, the way in which you find the parity is by multiplying all these wave functions. But again, if you have a closed system, then all the parities are going to be even, and only the parity of the unpaired nucleon is going to matter. So, the overall parity will be given by the L minus 1 to the power of L, where L is the at orbital atomic number, or this SPD corresponding to the unpaired nucleus. So I would say that again, these are all kind of fairly advanced concepts. A 2 hour lecture does not do justice to any of them. For further reading, I've put this. So I would say that if you want to understand more about harmonic oscillator, angular momentum addition, for example, this how this L minus S, L plus S, and all that, which is a chapter of itself, I would say that you can go for Griffith's Quantum Mechanics textbook, which is a very good textbook to get hold of your concepts. And along with that, I would say that you can look at Zetley's book. Zetley also has good explanation of concepts, but it also has a lot of solved problems, and that helps you to learn quantum mechanics in general. model. I think Zetli's chapter 4 or 5 is about angular momentum addition. And I remember doing those problems to really understand this concept for the first time. The other thing I would suggest, and I think this can hold for most of the course, is that there is a textbook on nuclear physics called Crane. This is the book that I used in my master's. It's a very well written book and it explains all these concepts, particularly chapter 5 of Crane's textbook is about nuclear models. It talks about the shell model in a lot of detail, and it will. If you want to read something to, if you feel like you don't understand the shell model and you have a little bit of background of quantum mechanics, I would encourage you to go and see Crane's textbook. These are all, textbooks. I'm sure you know how to find textbooks online. I will not say anything more about that, but yeah, please, these are all very popular textbooks. You will be easily able to find PDFs online if necessary, or use your libraries or something. Yeah. So I thought that finally, before moving to our problem section, this time we have had a long introduction, but yeah, before moving to the problem section, this is a figure I took from Crane chapter 5, which I just now mentioned. So you can see that here is a filled and empty filled states of two isotopes of oxygen, oxygen 15 and oxygen 17. And here they have said that the filled proton shells do not contribute to the structure. The properties of the ground state are determined primarily by the odd neutron. So here you don't even have to apply the sequence or anything. The already the states and how they are filled is given to you. I just want you to identify the spin parity for these two oxygen isotopes, and this should not take even 2 minutes. The answer is in front of you. So please write it in the chat so that we can move on to doing the actual questions of today that were assigned. I mean, the answer is here. You don't have to do, I already have which are the filled states and where does the unpaired neutron lie. So it should not even take a minute for you to write the answer. So please write the answer in the chat so that I know you're following the lecture. Hello. Do people not understand what the question is? Is there any doubt about the question? You don't have to do the sequence. It's already given to you in this figure. Please put the answers in the chat. I am waiting all the questions to do as well. Huh, yeah, okay. I see 1p half and 1d 5 by 2. Yeah, I mean, obviously that is correct. That is given in the figure itself, right? 1p half and 1d 5 by 2. I want the parity and the thing. So please give me the parity also of the state. Try to give me a complete answer. And I don't want the state, I want the spin parity. So when I asked you for state, you have to give 2p half, 2p 3 by 2. Here I'm giving asking you for the spin parity. So like how Vivek wrote half minus. So Vivek, please complete your answer. Write it for 17, oxygen 17 also. So 1p half and 1d 5 by 2, you can see from the figure. There is nothing to ask if it is correct. That's why I was surprised that you guys are not answering, because the answer is given in the figure. Half minus and 5 by 2 plus. Okay, good. Minus. Okay, why have you left it as minus 1 to the power 1 and minus 1 to the power 2? You can write it down, right? Minus 1 to the power 1 is minus 1 and minus 1 squared is plus 1. So don't make me do your 2. Yeah, don't make me do your maths, man. Okay, there's no step marks or anything. You don't have to show all your steps. Okay, but yeah, the point is that oxygen 15 is half minus and oxygen 17 is 5 by 2 plus. As some of your friends said, two of the people have answered out of 17. I hope the other 15 people also know how to do this. If anyone has any doubt in how this came, please write it in the chat. These are very important concepts, and you will definitely be getting some of these questions in your exams. Okay, I think we don't see any questions, so we'll go back to yeah, okay. Before we move to the questions, I just wanted to show a few interesting things that I kept, but I will not explain in much detail. So this is the demo, this is a simulation or like a website where you can like play around with how many protons and neutrons there are, and especially magic number, and you can see how the states are filled. So you can see here there's magic number of neutron and magic number of proton, and because of that the proton states are filled, so they are all paired together, for example, so that makes them stable. And you can play around with all of them, and you can see how at these values actually all the nuclei are paired. You can actually verify that, because it might not be obvious by just seeing that, for example, 82 is a magic number. We can see, if you see it like this, it's easier. This is another demonstration where you can look at how the square well and the Wood-Saxon potential, which is a more realistic potential for the nuclear shell model. Both of them can vary, like, and how much they vary for a given atomic mass number. And, that gives you an idea of how much the variation is there. And finally, based on, I told you that I will tell you about where nuclear shell model kind of fails. So the problem is that nuclei can get deformed and they might not maintain spherical symmetry. In which case we get deformed nuclei, and those are not exactly captured by the shell model. So there, those are the kind of like limitations that are there. And when it comes to stable nuclei, as I said, for the lighter elements, you see that Z is equal to N kind of elements are very stable. And but for heavier nuclei, you will see that it is actually more number of N when compared to Z is stable. Like one more of, if you go beyond like atomic number 100 or something, you will see that more of them have more number of neutrons. And the way that this is all often captured in this kind of plot, and this is a plot of neutrons with protons, and how the stability goes. So all this dark blue region is like called a sea of instability, and the rest of it as the stable. You can see how the stability matters, and there is like a island of stability for the super heavy nuclei. And there's a very nice video about stability and also very heavy nuclei, and also about how new elements are discovered, and about actually a scientific fraud which happened when a person claimed to have found many new nuclei, but it was actually a false claim that he had fabricated. And so obviously this is a non-academic video, this is not going to help on your exam or anything, but it's like a 1 hour video. It's very well made, and the beginning of that video they explain all this nuclear physics thing. So I thought that if you have some free time, you can watch it, because I think it's a very well made video. And yeah, I just wanted to share that with you. So with that, finally, in the last half an hour, we can move to doing some questions. So again, I pick up the questions from your previous year's assignments and so on. So you will find that a lot of the questions are related to things not only from this class, but from previous classes as well. Please keep a calculator or pen and paper ready so that we can do the questions together. We are already, falling behind on time. So please answer in the chat, and that will be very helpful. Okay, so this is the first question. What is the minimum temperature required for the fusion of a proton with a neutron classically? This is a question that we have discussed in last week's tutorial. I'll give you 2 minutes to answer the question. I don't see any answers yet in the chat. I'm just monitoring. Okay. Yeah, I see one answer in the chat, T9 6.14. Any other people to answer? I'll give you 1 more minute if anyone else is also working it out. Anyone else? Anyone who does not know how to do this question? Please put that also in the chat if anyone doesn't know how to proceed. I think you should know by now because these are things we have discussed over and over again. I don't see any other answers in the chat. Anyone else? Are you all solving or is everyone solving? Does anyone not know how to do this question? Please put your answers in the chat if you're solving. Do people not know how to solve this? Please, like, give me some feedback. Are you solving? Are you not solving? Otherwise, it's difficult for me, right? Okay, if people are not going to give the answer, I will give the answer. So your friend was correct. It is T9 6.14. Okay, Arvind. Okay, you don't know how to proceed. Fine, thanks. So if people tell me if you don't know how to proceed, then only I will be able to explain. So again, what did we find last class? We discussed that fusion requires very high temperature classically, and that's what this question is kind of illustrating. We require something like 6 billion Kelvin to um, fuse atoms together, fuse hydrogen together to form helium. But we know that the interior of the sun is hot, but it is not that hot, right? So what actually helps us to do the fusion reaction is quantum tunneling. So this I've explained a lot in last class. So quantum tunneling is a quantum mechanical effect which helps us to explain the fusion reaction. Now, when I say classically, how does the fusion happen? Then we have to care only about something called the Coulomb barrier. So again, this was discussed in last week's class. If you have some doubts, please go and watch last week's lecture or look at the slides. But essentially, what is a Coulomb barrier is the fact that when I want two protons to fuse or when I want hydrogen to fuse, there is a Coulomb repulsion between them because like charges repel. So classically, if I don't consider any quantum mechanical effect, I need both the hydrogen to fuse together by overcoming their repulsion. So essentially, the energy required or the temperature required is the energy to overcome this classical Coulomb barrier. Okay, is this fine? So after that, it's just a matter of substitution. So you can see that energy is given by Z1, Z2 E square by R. And here Z1 and Z2 are the proton numbers. So essentially, how many protons are contributing to the Coulomb barrier? E squared is given by, it's a constant, and R is, as we discussed today in the liquid drop model, R has a dependence on A. And here we are only talking about the fusion of two protons. So sorry, fusion of two protons. Or sorry, we are talking about fusion of a proton with a deuteron. So that's why it will be 1 and 2 for the atomic numbers, but both the, mass numbers, but the proton numbers are going to be 1 because deuteron is just a proton with an extra neutron, hydrogen atom with an extra neutron. If you substitute, you will find that the energy comes to be around 530 keV, and that when you convert to a temperature comes to be 6.14 into 10 to the power of 9 Kelvin. So here T9 means whatever value you get into 10 to the power of 9. So, does anyone have any doubts with this? This was actually covered in last week's class. I've given a quick explanation, but if you still have doubts, I encourage you. As I said, all the YouTube videos are recorded and put on YouTube, and the slides are shared. This is for your convenience. So, you should go and, definitely look at them if you still have some doubts in these concepts. Okay, so I think I have explained. If is there any further doubt? Okay, someone says no. So I'm going forward with the next question. And yeah, if you don't know how to solve it, please don't feel shy. Please just say I don't know and I will explain. Anyway, I will get to the solution. So don't worry about it. Okay, it's clear. Fine. The next question is, which nuclear reaction is responsible for the very long lifetime of the sun? So this is, should not take you time since there is nothing to calculate here. So I expect everyone to answer. Okay, someone says D. Others, there's no calculation here, so don't take time to answer. Okay, someone says B. D, B. I see people are talking about D and B. I want a few more answers because right now D and B are both tied. Okay, one more D. Others, there are 19 people in this meeting. Others, please give your answer. Okay, I see one more D. I'll give 1 more minute for people to answer. Again, there's no calculation, so people don't hesitate to answer. Other people, are you answering? Okay, I'll move to the answer. The answer is D. So as I told you, weak interactions are what takes a lot of time. So I think one more person said B. So maybe you got confused. But as I said, weak interactions usually take much more time when we compare with other forces. So if you remember, I told you that whenever a neutrino shows up, you can kind of call it as a weak interaction. And this is the first step of your hydrogen cycle, right? Your pp cycle. So you, as I showed you in the very first slide, I think, yeah, you can see that this takes around billion years, and then the rest of the steps take place very fast. So actually, it is this step which makes the lifetime of the sun very long, because these fusions takes a lot of time. Okay, so weak interactions usually take place with a lot of time. So that's the answer. So I hope this is clear. If anyone has any doubts, please put it in the chat. But for now, I'm moving to the next question. This was a long, okay. So this is a direct application of what we did. And I have even provided you with the shell model so that it becomes easier for you. So the question is, what is the spin parity of 43 calcium nucleus in the ground state according to the shell model? I have given you a diagram of the shell model also, but I encourage you that if you want to do it properly, please don't look at the diagram. Try to do it on your own. And then if you have any doubt, you can consult with the diagram, because that will be better for you from the point of view of exam. Someone has raised their hand. If you have a question, please go ahead. Is there some way to compare the time scale within 2 week off the top of, there must be some way, but it will be depending on, the way that you compare the time scale for any interaction, right? Cross section, all that will be there. But if you notice in this question, the previous question, I'll just go back. Sorry. Yeah, if I go back, the previous question, the rest of them were all not weak interactions. So it gives you a very direct question. So if they're going to ask you a question like this, they will ask you something where it's very clear what it is. Okay, so other than that, generally how to find reaction rate and time, all that. So I guess in that sort of way, off the top of my head, I can't think of a snappy way in which you can do it. But yeah, it will be there will be some way to do it. But generally the idea here is that the weak interaction scale is much higher when compared to everything else. Okay, so someone has given 5 half plus. Anyone else? Yeah, so Vivek, your answer is that, there is a way, but I think it's not important for the details of this course, particularly. Yeah, cool. Any other answers in the chat? Again, this question you should be able to do. We discussed it in detail. Again, remember that it is the valence nucleons which play a role, and not the filled shells. Any other answers in the chat? I don't see anyone else answering. Are you guys solving? I hope you are solving. I want everyone to answer this question because, yeah, it's important. Yeah, okay, okay, good. Okay, I see 3 answers. More people, please answer so that we can know which is the right one or have a majority. Okay, I'll give you 2 more minutes in case some of you are still solving. Okay, okay, I see people are saying 7 by 2 plus, 7 by 2 minus, 5 by 2 plus. Okay, yeah, okay. Someone changed their answer to B. Anyone who's still solving, or should I go to the answer? 3 by 2 plus. Okay, I'm going to go to the answer. The answer is, I think, some of you said 7 by 2 minus. So, again, this is a straightforward way of putting this. So, the important thing that is not mentioned here is what is the proton number of calcium. The proton number of calcium, or the Z for calcium, is 20. So, that should immediately tell you that number of protons will not matter for my calculation because they are, fully filled, right? So I only have to worry about the neutrons, which is 43 minus 20, which is 23. So I have to just fill in the shell according to the neutrons. And when I do that, you can see that, let us fill the 23 neutrons into the shell because the protons are already filled. They are already in a magic number configuration. And this is just the filling has been done according to the shell model, which I have already shown in the previous slide. So you can see that the filling has happened here. Yeah, so you can see my slide. So you can see that the last orbit is 1f7 by 2. So the last unpaired neutron is in the configuration of 1f7 by 2, and it has spin 7 by 2. Its parity is minus 1 cube, which is minus 1. And why does cube come? Well, cube comes because of this. F orbital has L is equal to 3. So yeah, that is the answer. And I think some of you got it. Those of you who didn't get it, please try once more and verify that you are able to get it. These kinds of questions, they are very easy to ask. So people will be asking them. It's a good idea to have it in mind. And as I said, if you memorize up to even 28 or 50, then it will be good for you. I don't have any snappy tricks to remember it, but I'm sure someone on the internet will have them. Okay, so that's about this question. Next question. Okay, so this is something about resonance reactions. So, but it is related, very much related to the things that we discussed in last week's class. Okay, so this is a little lengthy question, so I'll give you some time, or not lengthy, but you will have to remember some formulas or look back to your notes and see last week if you can see some formula which is relevant. So the question is that there are four hypothetical narrow S wave resonances that are occurring in the low energies at these particular energies, which are resonance means it's more favorable in those energies. So which resonance do you expect to dominate the reaction rate when it is T is equal to 20, sorry, 0.02 gigakelvin. So giga is 10 power 9. So you need to use concepts from last week's class. So if you have your notes or those things, you can refer to them. Or if you remember, that's great. That's the best actually. I'll give you 5 minutes to solve this because this is a little long question. As you get the question, please, not long, you just need to find those formula or remember it correctly. Once you get the answer, sorry, please put it in the chat. Are there any answers in the chat? So I can say that if you are confused about how to proceed, I will tell you that you can look at your gamma peak value formulae, and that will be helping you here, because gamma peak tells you about what are the energy window for which a reaction happens at a particular temperature. And here they are exactly asking you what are the energies which will dominate for a particular temperature. So you have to match the resonance energy with your gamma peak energy. So now I have given you how to do it. Now I just go and search for the gamma peak energy and those different calculations that we did and try to solve it. I'll give you 2 minutes. Does everyone understand how to do the question now, in case anyone didn't know how to proceed? Hello, did everyone understand the explanation I gave about how to proceed with the question? Did everyone understand, or should I explain it once more? If I want to explain it once more, please say it in the chat. Otherwise, it's difficult for me to understand if you have really heard me and understood me or not. Please respond yes, no, something. Yeah, okay, good. Okay, cool. So please proceed with it. I'll give you 1 more minute and then I'll move to the answer because we are reaching the end of our session and I have few more questions to go through. Okay, you want me to repeat? Okay, so how do you find the optimal energy window at a given temperature? We discussed this in great detail last time. It's using the Gamma peak. So I'll do one thing, I'll just go to the answer because we are also running out of time. So essentially, last week we talked about Gamma peak. If you don't remember, please go and watch last week's lecture. The Gamma peak gives you the optimal or the good energy range where the reaction happens for a particular temperature, right? And gamma peak has two things. One is the peak energy and the peak width. And we've learned how to calculate both of these. Now, in this question, they told you that this is a resonant reaction which happens at particularly four values of energy. It peaks, the resonance happens, right? So they want to know which are the two resonances that will play a role in a particular temperature. So for that, we need to know, we need to match the gamma peak and these energies. That's what we need to do. Okay. So now if I go to the answer, I think people could not know how to solve it or you're taking time, but I don't have time also. So I'm moving to the answer. The answer is 30 keV and 50 keV will dominate. As I said, the reason is because of the gamma peak. Last time we already discussed these formulae. So if you have doubts of what this figure means, please go and watch last week's lecture. This is the reaction which is given to us. Sorry, I'm saying neon. Neon plus reacting with a proton to give sodium at the release of energy. And you can see here Z1 is 10 because neon has a atomic number 10. Proton is of course Z2 is 1. You need the reduced mass which is 20 by 21, and T we have to represent in terms of T6 because that's what's in our formula. So 0.02 gigakelvin is 20 million Kelvin. And if you now substitute all these values, you will find that the peak energy comes to be around 40 kV. It's actually like 38 point something. And the delta comes to be around 20 kV. So if you now put you know that the gamma peak is between basically E minus delta by 2 and E plus delta by 2. So if I check that, you see that the gamma peak lies between 30 kV and 50 kV. So this is where the optimal reactions happen. And that corresponds to 30 kV and 50 kV peak of the resonant reaction. Okay, so this is how to do this question. Even though it's not mentioned gamma peak anywhere, you should expect that when a temperature dependence is given, you have to find the optimal reactions through the gamma peak method. So does this make sense to everyone? Does anyone want me to explain again? Otherwise, we can go to the next question. Please give yes or no in the chat. It's difficult. Already, I also want to end. Okay, good, good, good. Got it. People say got it. If you don't understand, please go and watch Gamma Peak lecture again. It will make everything clear. Okay, I'm going to the next question. Okay, again, this is a resonance question. So I was focusing this week on the shell model, but resonance is also an important thing which was covered in your this week's lectures. So please see if you can do this. If you don't know how to do this, please put it in the chat. I can show you the solution. But please try to at least think about how to do it. So they have given you a resonance state at some temperature, but the resonance was wrongly measured. So then what is a factor by which the resulting narrow resonance rate is higher? So you have to use a formula for resonant rate, which probably is discussed. Okay, someone says 1.59. Anyone else? Any other answers in the chat? I'll give you 1 more minute and then I'll move because we have to end the session. If anyone has any answer, please put it in the chat. I'll give you 1 more minute. Okay, I don't see if anyone is solving, or should I move to the answer? Yeah, I don't see any response, so I'm going to move to the answer. The answer is 1.59. So the one person who answered has done it correctly. Very good. Uh, yeah, okay, I'll show. So if you don't know how to solve, just tell me how. So then I will know whether you're solving or not. So basically, this is the reaction rate for narrow resonances. This was derived in the class. I have not discussed it today because I already had to discuss about shell model. So if you have any doubt, please go to sir's lectures and look at it. And if you want me to cover this, I can maybe cover it in another class. Now it's given that your theoretical value is 1.2 and your measured value is 1.3, and they want you to find how much is it overestimated, right? Or what is the ratio between them basically. So you know that all of these are basically constant, 2 pi, this factor and all that. So it's really only the e power that is going to contribute to your thing, because everything else is a constant for a given reaction. So when I find the ratio, I find that all the other terms cancel out and I just have to find the ratio between. So by the way, there's e power minus. Okay, I think the font, it's not seen properly, but it's e power minus of theory by things. So that's why. Okay, so just be careful with that. So, so this is how to do the question. Okay, I hope there is no confusion. I'll go to the next question now. So this is a question which is very a direct question which you should do. Please, I'll give you 5 minutes to 2 minutes to do this question. I hope you guys are solving. Does anyone know not to how to? Okay, okay. I see 6.67. Someone has given the answer. Anyone else? Any other answers in the chat? Anyone else who does not know how to solve this or something? This I will not. I will be very upset if you don't know how to solve this. I think this is a fairly straight question to answer. Okay, I don't see any comments or questions. I'm going to move to the answer. The answer is actually 8.67, and this is how you do it. So basically, if you write the reaction, it will be like lithium 7 plus proton gives 2 alpha particles. So you have to find the energy release in the normal way, which is where you just sum up and subtract the total thing, and then you multiply by 931. And I've already explained why 931 comes, is because when we do E is equal to mc squared, this represents the c squared part, right? And they have asked actually the energy taken away from each of the alpha particles, and to balance it we need two alpha particles, right? Because lithium has 7, proton has 1, and each alpha particle is 4 atomic number, I'm saying. Sorry, mass number, I'm saying. So we need two alpha particle to balance the reaction. So if you want to find the energy taken away by each alpha particle, we have to divide it by 2. Is this clear to everyone? I hope after seeing the solution, at least you will respond in the chat. Yeah, okay, cool. So you are able to understand, I hope. Again, please try these questions. These are questions you have done already. They might be asked in slightly different way. Doesn't mean that you don't know how to do them. Just try to think a little bit. Okay, so this is calculate the mean lifetime of deuteron against destruction via the this reaction for this given temperature, and the density and all that is given. They've also given you the reaction rate. So I think this also comes from maybe 1 or 2 lectures ago. So I'll give you 2 minutes to find the formula or remember the formula and solve it. Any answers in the chat? Okay, I see someone has said A. Others? Others? Anyone? Okay, I see someone else said 2 seconds. Any other answers in the chat? Okay, one more person says A. So yeah, the answer is actually B, 2 seconds. I think one of you got it. So this is again, you have to do it in the usual way, which is where the time period is basically you have to find the reaction rate. So this is a reaction rate per particle. So you have to consider it weighted against the molar weight and all those factors. This we have already explained in a previous class. And of course, rate inverse gives you the mean lifetime. And when you do the calculation, it turns out to be 1.99, which is nearly 2 seconds. Okay, so who got point 2, please check your calculation. Maybe you missed a factor somewhere. I think the formulae by now you should know, maybe some calculation error. So just check that once. Okay. This is the next question. Detection of 1.8 mega electron volt gamma ray shows presence of which element? Again, this is something covered in your lectures. So this is emitted by aluminium, but which isotope of aluminium? In a particular reaction, a decay reaction of aluminium, but which isotope? Okay, I see people saying C. This is again not a theory question, so please people answers quickly. Yeah, okay. I see one more C. Any other answers? Okay, we are nearing the end of the session, so I'll just move to the answer. This is aluminium 26. Aluminium 26 decay gives you 1.8 MeV gamma ray, and yeah, that shows the presence of that element. I think this was covered in your lectures. So yeah, this is the last question for today. At the energy of 1 keV, which is given by T9 of 0.01, what is the order of the tunneling probability? Again, this is something that was covered in your previous week's lectures, week 4, and we have also discussed it in the class. So if you can find those formulae, try to do it. Okay, someone says B. And yeah, we have actually discussed this particularly in the class, this problem, when we talked about quantum tunneling and calculated probabilities. So you don't have to calculate also if you remember the lecture. Okay, I see B. One person says A, but lots of B. Any other answers? Okay, I think I can move to the answer because it's getting, we have already passed time. The answer is B. We remember before calculating itself, if you remember that we compared the Coulomb barriers 10 power minus 200 something, 70 or something, and then we compared with quantum tunneling probability, which is around 10 power minus 10. So that was for proton fusion. And of course, if you do the actual probability that comes from this formula, I think we discussed this last time, can be written in this form, which you have seen in your lectures. And if you take the exponential, you'll find that it's something of the order of 10 to the power of minus 10. So that is the answer. So yeah, that's the last question that I had, I think. So that's all for today. So any doubts from today's class? Any other doubts? Today I focused on nuclear shell model because it's a little, maybe a little difficult to visualize at first, but it's a very powerful model. It won Maria Gopert Mayer a Nobel Prize. She was the second woman to ever win a Nobel Prize. And she remained so for 50 years or so, until 2018, if I remember correctly. So it's a very powerful, insightful model, and it has been used in nuclear physics everywhere. So yeah, I see someone has said no doubts. So if there is nothing further, we are already 5 minutes past time. So we can end the session today. You guys can have a nice night. I don't see any other questions, so I'm going to end the call. Show the answer of question 8. Don't worry, like all the slides will be shared with you also, so you can see them that time. But this is the answer. It's decay of aluminium. I hope that is okay. Does anyone have anything? Yeah, okay. Okay, fine. I think that's it. Okay, thanks everyone. Have a nice night. Okay, we'll just stop sharing. Yeah, bye. Bye everyone. Recording.